Now let's look at some of the values from the example on the oscilloscope. The AC voltage from the wall outlet can be brought into a transformer, which can be used to decrease or step down the incoming 120 volts to a more usable level.
Here, a 1,000 ohm resistor is being used as a load. Let's attach the probe leads across the load. Place the volts per division selector on 5 volts. The peak voltage in this case is equal to 3 full divisions and 4 minor divisions. Because each full division is set to measure 5 volts, the minor divisions will represent 1 volt each. To find the peak voltage, just add the values of the divisions together. 3 full divisions at 5 volts each is 15, plus 4 divisions of 1 volt each equals a peak voltage of 19 volts.
Keep in mind that there can be a positive peak voltage as well as a negative peak voltage.
In this example, the peak-to-peak voltage is equal to 6 full divisions and 8 minor divisions. With each full division representing a value of 5 volts, this makes a total of 38 volts peak-to-peak. Notice that this is twice the peak voltage.
Let's compare the oscilloscope readings with the readings on a digital multimeter or DMM.
Begin by connecting the DMM across the same load and selecting the AC voltage scale. The meter reads 13.43 volts, which is different from what we found on the oscilloscope.
Remember, the oscilloscope indicated the peak voltage. Let's convert this to a RMS voltage.
0.707 volts times 19 volts equals 13.43 volts, which is the RMS value indicated on the meter.
Let's check the peak-to-peak value by using the voltmeter readings.
First, convert the original RMS value to peak. 13.4 volts divided by 0.707 equals 18.95 volts peak. Now double the peak value to find peak-to-peak, which is 37.9 volts, or about 38 volts. Stop the tape and review this section again if you have any questions.
Now, let's see how Ohm's law works with AC circuits.
As mentioned earlier, Ohm's law is as useful in determining AC values as it is in the calculation of DC quantities. This is because in a purely resistive circuit, voltage and current are always directly proportional. Conversely, resistance and current are inversely proportional. The only conceptual difference between the AC and DC applications of Ohm's law is that while the voltage and current values in a DC circuit can be expected to remain constant, in an AC circuit these values are constantly changing. But for an instantaneous moment in a given cycle, the value of the current flowing at that instant is directly proportional to the magnitude of the voltage at that same instant.
Since all direct current rules and laws apply to alternating current resistive circuits, the AC power may be calculated from the measured voltage and current.
If the instantaneous values of voltage and current are multiplied and plotted, an AC power waveform is constructed. Keep in mind that whenever two positive values are multiplied together, the result is positive, and whenever two negative values are multiplied, the result is also positive. During the first half cycle of voltage and current, the power curve is in the positive direction. During the second half cycle, the power waveform continues in the positive direction. In purely resistive AC circuits, that is, circuits without any inductance or capacitance, the voltage and current waveforms will intersect the zero axis at the same time and will reach their positive and negative peaks at the same time. When this happens, the voltage and current are said to be in phase. For these types of circuits, the entire power waveform will be above the zero axis.
AC power can be measured directly in a circuit with a wattmeter.
A wattmeter has a scale calibrated in watts. On this meter, it's the bottom.
Stop the program and complete activity number 4. When finished, continue watching the program.